Okay, so this unit on outcome 3A, we're looking back to kind of rational expressions. We are looking at equivalent expressions. So we're basically looking at equivalent fractions, but in the process of putting polynomials in there, making it a little bit more where we're going to have to pull in the factoring pieces. Oh, remember the factoring pieces from a while ago? That's going to come back to haunt us a little bit. Today, though, we're not going to really necessarily get into the factoring side of it. We'll save that for Monday. But we will talk about just the basics of rational expressions and kind of some restrictions and things that can kind of come into play. So if we think about rational numbers, it's simply just a fraction, you guys. You're going to always have a fraction. So if I think about a fraction could be as simple as 0/3 or 2/3 or 1/3 or 1/4, whatever it is. But notice that we can never, ever have a 0 in the denominator, okay? That's what we consider to be undefined. So one of the things that we have to take note when moving forward through when we're working with rational expressions is that we have to think about what we call non-permissible values. So this really means what values cannot be in the denominator where we'll get a 0, because we can't have a 0 in the denominator, okay? So that's basically our first thing, is to identify non-permissible values. And all that is, and a non-permissible value will only show up if you've got a variable in your denominator, okay? So if I look at the first one, and I look at 3x/4. Well, it's a rational expression. It's simply, it happens to have a variable in the numerator, and it's got a whole number in the denominator. So it's really, you've got a numerator and a denominator. The denominator isn't 0, so it's not an undefined. So it's just a regular rational expression. Now, if I pop over to the next one, I've got x², this is a squared, minus 6x minus 7, and it is over, it's got a denominator of x plus 5. Now, this is problematic down here if we have a certain value that we put in for x where we would end up getting 0 down here. So a non-permissible value in this instance down here, the only value that I could put in here to get 0 would be basically taking the 5 but making it negative, right? We would 0 that out in here. So a non-permissible, in this case, non-permissible value would be x is equal to -5, because that would mean I would be getting a big 0 down in the bottom, and we can't have a 0 in the denominator, okay? Questions on that?
No.
Okay, so basically then when we start to look at any of these, so if I look at 7/x, and you are asked to determine what the non-permissible values are, you're asked to identify them. I'm going to look at this and I'm going to say a non-permissible value, I would determine that by taking whatever is in my denominator. So I'll take whatever's in the denominator and I will let it equal to 0. I'm going to use it to set equal to 0 to find out what that x will actually equal. Well, in this instance, if I take the x and set it equal to 0, I actually get that my non-permissible value for this particular fraction would be x. X can't equal 0, because if it equals 0, I would create an undefined fraction, right? So I would be saying that my non-permissible is where x can't equal 0. Okay, so just to take note, an equal sign means equal, and an equal sign with a line through it means it can't equal that. So in this instance, we're going to always, when we talk non-permissible values, we're always going to say it's got to be an x can't equal whatever that value is. We may set it up as an equality so we can identify what the value is, but our final answer when we're trying to find our non-permissibles is it's got to be not equal to. So in the second one, when I start to look at 5 over x minus 2, again, I'm going to take that denominator that I've got. So x minus 2 is in my denominator. I'm going to set it equal to 0, and I solve for x, which means I'm going to add the 2 over, and I'm going to find out that x equals 2. So that means my non-permissible value for this one is x cannot equal positive 2. Because if I end up putting a 2 in here, I'm going to get 2 subtract 2, which is going to zero me out, which means I'm going to have a denominator of 0, which doesn't work for us. So you can always take your non-permissibles, plug them back in, and see if it actually holds true to what, so you know if you've calculated it right? So if you're non-permissible, whatever you've picked, you got to be able to put it back in. If it zeroes out, you know you've done it right. Okay, so the next examples then, all they're doing is they're simply asking you to find the non-permissible values. So again, non-permissible, you're only ever looking at the denominator. I don't care about the numerator, okay? I can have a 0, I can have it equal to 0 in the numerator. It's the denominator that I can't have equal to 0. So basically I look at both of these. I've got two factors here. I've got an x minus 2, and I've got an x plus 5. So basically I have to take each of those and set them equal to 0, because I want to find out, because here's the thing. If I zero this side out, the whole bottom is going to be 0 times whatever this value is. It'll still equal 0. If I zero this side out, again, 0 times this is still going to equal 0. So I'm going to end up here with the potential of having 2 values for x that could potentially zero out the denominator. So in this case, again, if I added the 2 over, I would get x can't equal a positive 2. And in this case, I subtract the 5 over, and I'm going to get x can't equal negative 5. So I end up having 2 non-permissible values in that situation. Okay, so the next one. Oh, you guys, I lied. I'm sorry. We do have some factoring to do. So there's a couple scenarios that can happen here. So again, you're asked to find the non-permissible values. Now again, I'm only going to the denominator. So in this instance, I have x squared minus the 49. So I could, 2 different ways to approach this. I could take this and I could say, hey, I could factor this. Okay, or I could take this, 2 terms like this, and I could say I've got x squared minus 49 and set it equal to 0. If I add the 49 over, I get x squared is equal to 49. I take the square root of that and I get 7. But remember, the square root, when I take the square root of a 49, I actually get 2 options. I get the positive version and the negative, right? Because a negative 7 times a negative 7 will give me a positive 49, and a positive 7 times a positive 7 will give me positive 49. So in this instance, I'm going to get my non-permissibles to be either positive or negative 7. Now you can treat this differently. I said factor. Well, if I ended up factoring this, if we recognize this, this is a difference of square. So if I factored this, I would really get x plus 7 times x minus 7. And then I could technically set that equal to 0. In reality, what I've got is I've got each of these to equal 0 then. So I'm looking at x plus 7 equals 0. I've got x minus 7 is equal to 0. So same thing, I'm going to come up with x is equal to negative 7, x is equal to a positive 7. So my non-permissibles still hold true. They're the same thing. It's just 2 different processes to figure it out. Either factor it out and then break down and figure out, isolate each of your factors. Or in this instance, a difference of square you can set equal to 0 and solve by adding that number, that value over. It works because you don't have a middle term in here. okay? You don't have, this isn't as a trinomial, like it's not set up like this, okay? If it's set up like a trinomial, then we're gonna do like what we're gonna do down to this one. Okay, so this right now on this next example is we really have p squared minus p minus 12 on the bottom. So that one I do have to factor, because if I set p squared minus p minus 12 and set it equal to 0, I could go through, technically I could go through the whole process of actually completing the square and moving through all of that, but you're going to make way more work for yourself doing that. So my suggestion for this, factor, factor, factor. So factor the bottom. So if I've got p squared minus p minus 12, this is going to be your little refresher course today. I am looking for two numbers that multiply out to negative 12, and it's got to add up to negative 1. So in that instance, they've got to multiply out to negative 12. What are we saying?
Oh, I just did something on my phone. I was like, what the heck?
Okay, so I'm looking at, well, stop clicking buttons already. Let's say, I think we're going to be working with minus 4 and a plus 3, because a negative 4 times a positive 3 is going to multiply out to the negative 12, and negative 4 plus 3 is going to give me the negative 1 that I need. Okay, so in reality, those are my two factors that I've got in the bottom. Now that I've done that and established that, yeah, I'm essentially setting the whole thing equal to 0, which means each of these factors I set equal to 0, and I solve for p. So p in this instance can't equal 4, and p in this instance can't equal negative 3. So those are my non-permissibles. So yes, I was mistaken. You are going to have to do some factoring, which is okay. That'll get us into a kind of a good refresher for moving forward on Monday. Okay, our next example. Any questions with that?
No.
Okay, so then our next one is we've got 4a over 3bc. Okay, so same thing here. The difference is, so when we factor this, we actually create these two terms that are being multiplied together. Well, same thing happens here. We just don't have a plus or a minus happening with our b and our c in here. So really, I'm taking this whole thing, 3bc, and if I let it equal to 0, well, if I want to know what b is, that means I'd be dividing both sides by the 3 and the c. Well, 0 divided by anything is still going to leave me with 0. So if I do the same thing and want to take that 3bc and solve for c, same thing. If I divide both sides by 3b, I end up getting 0 divided by 3b, which gives me 0. So my non-permissibles are b can't equal 0, c can't equal 0. So same thing holds true when we work through these, okay? Which makes sense. If I put a 0 back in here on the bottom, this whole thing would become 0. So it doesn't matter if I put a 0 in for B or if I put a 0 in for C, it's still going to 0 it out. So these end up being my non-permissibles. Questions?
No.
Okay, so let's go on to the next. So the last piece then, what I wanted to do today is to talk about equivalent rational expressions. So when I think about equivalent rational expressions, it's the whole idea of hey, I've got a half. If I've got a half, another equivalent rational expression to a half means that I would times my numerator and my denominator by something, by a 1 of some sort, which means if I multiplied top and bottom by 2 over 2, that would mean I would get 2 over 4. Well, 1/2 and 2 over 4 are equivalent fractions. I could take 1/2 times it by 4 over 4. I would get 4 over 8. Okay, equivalent fractions. So it doesn't matter if I take up my fraction, whatever my fraction is, and times it by a 1, essentially, because 2 over 2 is just the equivalent of saying 1, or 4 over 4, whatever I use, whatever that fraction is, it's got to be the equivalent of a 1, essentially. Because if I do that, as long as whatever I multiply, top and bottom, it doesn't affect my fraction. It doesn't change the value of that fraction if I'm multiplying the same on the top and the bottom. So that's all an equivalent fraction is you've just got to be able to multiply the numerator and the denominator by the same value. So in this instance, I can do that to a polynomial expression, like one that has variables in it. So like 7x over x minus 2. Well, I can multiply that by a value of 1. So instance, if I said, hey, I'm going to multiply it by 2 over 2. So if I look at this and say 7s times 2, that gives me 14s. Now, if I times the bottom by 2, remember, when you times the bottom by 2, you're distributing that 2 to both things inside. So that's really going to leave me with a 2s minus 2 times 2, which gives me 4. Okay, so as long as, so then this piece here is an equivalent rational expression to our original. Okay, they are actually the same value of sorts. And you could figure this out. You could actually take and put a value in for s here. So if I put 1 in for s here, I'm going to get 7 times 1 is 7, and 1 subtract 2 is going to be -1. I'm going to get a -7 there for a value. If I put a 1 in over here, I am going to get a 1. So that's going to give me a 14 on the top. 2 times 1 is 2. Subtract 4 is going to give me a -2. 14 divided by -2 gives me a -7. So I know they are equivalent rational expressions. Okay? Does that make sense?
Mm-hmm.
Okay. So here's the next piece then. So then let's take, we're asked to take 8x plus 3 over x plus 2. We take this rational expression, and we want to make an equivalent rational expression in which the denominator is really that. Okay, so that means I have to think about, well, I started originally with an x plus 2, but now my denominator looks like this. Well, I'm hoping you're seeing that the piece that's been added or included in the denominator is this 5, and it's really getting multiplied to this x plus 2. So that means in order to make this an equivalent rational expression, well, if I'm multiplying the denominator by 5, I better be multiplying the numerator by 5, which would mean then I would be multiplying the top by 5 as well. So in essence, with this, I could look at this and say, well, okay, well, if I'm multiplying the top, I'm going to get not 14. I am going to get 40x plus 15. And on the bottom, I'm going to get 5x plus 10. Okay, so in essence, I could be looking at multiplying it out. For the most part, again, I could look at this piece and this piece and say, hey, if I plugged a value in, again, like a 1, and I should get exactly the same answer when I'm done. And that's kind of all there is to finding equivalent fractions. So it's basically understanding that if I'm multiplying the denominator by something, I better be multiplying the numerator by that same amount. Typically, I want you to get more used to keeping things more in a factored form and not multiplying it through for our final product when we get through this, because as we get into simplifying rational expressions next day, you're going to see a little bit of that too as we move forward. But technically, both are correct. Okay, questions on that?
Super. Go away.
Easy peasy? Kaylee, are you still awake? Okay, that is it, folks. So basically what I want you to work on for the next kind of probably from now until Monday, because we won't meet again until Monday. I think that makes the most sense at this point. You've got assignment 1 in that notes package. If you go back online onto Google Classroom, if you haven't printed it off, you can always take a look at that or look at it through your phone and practice some of those questions. And then on Monday, what we will do is we will go through the next part of this. So basically the next part of it is taking a rational expression and actually factoring it. So factoring the numerator, factoring the denominator, and then worrying about whether or not we can cancel things out, and then identifying if we've got any non-permissible values moving forward. But that'll be Monday's job. We'll worry about that. Okay?
All right.
So if you guys have no questions, then we're going to call our quits for today and do that. Again, if you guys, as you're working through questions or you're having difficulty with something, throw me a text and a picture and say, Cunningham, I'm having trouble with this. I don't understand what I'm doing wrong. And I will try and get back to you as quickly as I can with an answer. And if it's something that it requires a little bit more of an explanation, I might say, hey, meet me on Google Meet and we'll go through and we'll figure it out together. Okay? Is that fair?
Yep.
Okay.
All righty then.
If you guys have no further questions, then have yourself a fantastic rest of the day. Get outside and enjoy some warm weather.
Will do.
Okay. See you.
Yeah.
Yeah. Yeah.
Bye.